Well, this is lecture 22 of basic calculus 1. You remember in the last lecture we had discussed using second derivative for deciding whether there is a point of extremum at a critical point. So, we will use second derivative for something else today. It is about the deciding the shape of the curve. So, they are basically called concavity. So, that is what we will be discussing today. So, let us look at this picture. Here is a plot, that blue one you can see, it is a plot of y equal to 3 plus sin x. And of course, y double prime is minus sin x, which is plotted in pink. Now, look at this blue one, which is our function f of x, it is 3 plus sin x. So, when a curve looks something like this, looked from the x axis side, we will be calling that as concave down, and when it is looking something like this, we will say it is concave up. So, of course, we should define them rigorously, but this is just an intuitive idea that this one is called concave down and this one is called concave up. Now, in this plot of y equal to 3 plus sin x, you can see from 0 to pi over this interval, the curve is concave down, and from pi to 2 pi, the curve is concave up. So, you would say that concavity changes at x equal to pi. This is just intuitive idea. So, we will be telling how to decide about that. So, look at this when it is concave down. If you look at the tangents, so it will be something like this. So, all these tangents are having positive slope, right, and at a point inside. So, when it is maximum, there the tangent is having slope 0, it is a horizontal tangent. Then when you go to the right side, you will see they come this way. So, they are negative up to pi, this happens. So, that means it is positive going to 0, then from there it is negative. So, that means from 0 to pi, the slope of the tangent is really going from positive to 0 to negative, that is it is decreasing. And on the other side, you will see that it is negative, then it becomes 0 and then it becomes positive. So, which means it is increasing from pi to 2 pi. So, looking at that, we will be defining our concave up or concave down. We will say that y equal to f x is concave up on an open interval I, here it is open interval 0 to pi, if f prime x, which is slope of the tangent, is increasing on I. So, it is up, concave up, so it is increasing on I. Similarly, we will say that it is y equal to f x is concave down on an open interval I, if f prime x is decreasing on I, and at that point pi, the concavity changes. So, we will say that it is a point of inflection. That is, a point of inflection is a point where y equal to f x has a tangent and the concavity changes. So, these are the three notions we introduce with concavity: concave up when f prime x is increasing, concave down when f prime x is decreasing, and a point of inflection where a tangent exists and the concavity changes. So, we will be applying this because to some other functions, not for this only, where our derivative will give us the information how the curve looks like. That is the main idea. Okay. So, for that we can really, instead of looking at f prime how it is increasing decreasing, we can think of the second derivative. So, you see, if it is f prime x is increasing or decreasing, then there will be some sign change or some specific sign of the derivative. So, we will specifically show that if f double prime of x is greater than 0 on I, then what happens here? F prime x will be increasing. So, y equal to f of x is concave up over that interval. Similarly, if f double prime x is negative on I, then f prime x is decreasing. So, it is concave down on that I. And what about the inflections? Of course, f double prime x is positive on one side of x equal to c and it is negative on the other side. Then this point CFC on the graph is a point of inflection. So, we will not see x equal to c is a point of inflection, we would say that the point on the graph c comma f of c is a point of inflection. There the concavity changes either from up to down or from down to up. So, that is how it will give. So, at a point of inflection, say at that point in our earlier curve pi to f of pi, either f double prime does not exist or it vanishes. If it exists and assuming that it is continuous, it has become positive one side, negative one side. So, there it must be 0 because of intermediate value theorem, provided f double prime is continuous. But if f double prime c equal to 0, it does not mean that it is a point of inflection, right, because it may not have changed sign. So, changing of sign is important for the point of inflection. Like you take a constant function. So, you would not say that every point is a point of inflection because f double prime c is 0, that we want to avoid. So, we will say that f double prime does not exist or it vanishes, that happens at a point of inflection. But any of these will not imply that it is a point of inflection. To check that it is a point of inflection, we should find out what happens to f double prime x on its left, on its right of the point. It should change. That is what it is. Okay, so, let us apply it on one problem. Let us take the curve y equal to x square. It is a simple one, parabola type. It is concave up everywhere because y double prime equal to 2, that you can find y double prime 2, it is greater than 0. Therefore, it is concave of every, as you see it looks something like this. Okay. If you take the curve y equal to x cubed and go for its derivative, that gives us 3x square, again once more differentiation, that gives 6x. So, f double prime x equal to 6x, where it is greater than 0, where it is less than 0. If you consider from minus infinity to 0, x is negative, in that case you get 6x to be negative. So, this is negative on minus infinity to 0. Therefore, the curve y equal to x cubed is concave down on minus infinity to 0. And if you take x is positive, so f double prime x will be 6x, which is bigger than 0. In that case, whenever x is positive, that is on the interval 0 to infinity, the curve y equal to x cubed is concave up. Now, let us take another, say y equal to x to the power 4. So, in this case, f prime x is 4x cubed, f double prime x is 4 into 3, 12x square, right. So, where does it change sign? That is what we have to look at. It is 0 at x equal to 0, of course, but you take negative, x is less than 0 or x is bigger than 0, everywhere it is positive, right, except x equal to 0 where it is 0. Once x is non-zero, you will see that f double prime x is x square, it is really 12x square. So, that does not change sign near x equal to 0, that is from negative, from a immediate left neighborhood to immediate right neighborhood, you will not see that there is a change of sign, it is always positive. So, 0 0, that point on the graph is not a point of inflection, though f double prime is equal to 0 there. Okay, and since it is positive, it is always concave off at any point, of course, not at 0. Okay. Now, for the curve y equal to x to the power 1 by 3, we will see that f prime is equal to 1 by 3 and x to the power minus 2 by 3, and you differentiate once more. So, you get 1 by 3 into minus 2 by 3, which is minus 2 by 9 into x to the power minus 2 by 3 minus 1, which is x to the power minus 5 by 3. Now, we are considering this at x equal to 0, of course, this is not defined. So, it is not differentiable even at x equal to 0. So, for x not equal to 0, we are trying to see what happens for this. Now, for x less than 0, when x is negative, it is 1 by x to the power 5 by 3. So, that gives f double prime x to be negative. And if x is bigger than 0, that is x is positive, f double prime x is positive. So, 0 0 is a point of inflection, and from minus infinity to 0, it is less than 0. So, it is concave down, and it is bigger than 0 for 0 to infinity. So, there it is concave up, and 0 0 is a point of inflection. You can look at the graph, how does it look? This is x to the power 1 by 3. So, at 0 there is a point of inflection, concavity changes, it is concave up and concave down as you see. And here what happens? It is y equal to x fourth, as we have seen there 0 0 is not a point of inflection, there is no change in concavity, it is same. Okay. So, that is how we will be talking about concavity. If you look at all this information, whatever we have got, we have some idea about the shapes of curves. Suppose the curve is y equal to f of x. First look at the first picture here. So, once it is differentiable, of course, it is differentiable everywhere as it looks, there are no corners and it is smooth, you can differentiate once more time and there is no break anywhere. So, graph may rise or fall, something can happen. So, once you say it is differentiable, there are no corners and graph may go up, may come down and so on. In general, it might look something like this. But once you say that y prime is bigger than 0, then f prime x is bigger than 0 would say it is f of x is increasing. So, it will be only climbing up. The curve may look something like this. Still it can be OV somewhere, right, but on the whole it will be rising up, it will be climbing up. That is how it is an increasing one. And if y prime is less than 0, that is its derivative, then it will fall, but it can still be wavy, having rise and fall in there, but on the whole it will be falling. So, that is what if f prime x is less than 0. And when you come to double derivative, suppose your double derivative is bigger than 0, then y prime itself will be increasing. So, the curve would look something like this, it is concave up throughout, no waves, but graph may rise or fall, it may look something like this or it may look something like this, both are really concave up. So, it may be like this, one of this, but there are no wave in nature, there is no rising and falling in between. So, if y double prime is less than 0, then it will be concave down. So, it may look this way or it may look this way, it may increase, it may decrease, but it is concavity is downwards. There are no waves again, but throughout it will be concave down. So, it may rise, it may fall, it may be increasing, may be decreasing, but it would look something like this. So, it basically says about the shape of the curve. And if y double prime has an inflection point somewhere, then it may be concave up and then concave down, or it can be concave down and then concave up. It may also be looking like this, where y double prime changes its sign, that can happen, but not uniformly like other two which we discussed earlier in 4th and 5th. Now, if y prime changes sign, say here we do not know, it was y double prime changes sign. When y prime changes sign, if it changes sign from positive to negative, then there will be a maximum point, and if it changes sign from minus to plus, there will be a minimum point, local maxima or local minima. That is how it would look, curve would look something like this. And if y prime equal to 0 and y double prime is less than 0 at a point, so that means there is a horizontal tangent and y double prime is less than 0. So, it will be looking concave down. So, it will be looking something like this, again it will have a local maximum. Similarly, if y prime equal to 0 at a point and y double prime is greater than 0, then it will be concave up and it would look something like this. Again it will have a local minimum point. So, these are some classifications on the basing on the information from the derivatives. So, that is how the shape of the curves will be determined. Okay, let us solve one more example. Basing on this idea, really we can try to sketch a curve, how the curve looks like in which intervals. So, we will not take everything because R is infinite, but on somewhere where there will be inflection point or there is a maximum point, minimum point and so on. That is what we will be discussing. So, suppose we take the function as f of x equal to 1 plus x whole square divided by 1 plus x square. So, it is defined everywhere, x square is never equal to minus 1. So, let us see how to use the information on the derivatives. So, first thing is there are no symmetries here, whether symmetry around 0, symmetry about x axis or symmetry about y axis, nothing is there. Okay. Domain is the whole of R. Now, let us go to the derivatives. If you look at the derivatives, it will be 1 plus x whole square divided by 1 plus x square. So, it will give you 1 plus x square times derivative of 1 plus x square, which is 2 into 1 plus x, and then minus derivative. So, 1 plus x whole square into derivative of 1 plus x square, which is 2x, and this divided by 1 plus x square whole square. That will be the derivative. So, if you simplify, that would give 2 into 1 minus x square divided by 1 plus x square whole square. And similarly, you go for the second derivative, differentiate it again, you would reach here, it will be 4x into x square minus 3 divided by 1 plus x square to the power 3. So, 1 plus x square is cancelled. So, that is the derivative, first and second derivatives. Now, equating this f prime x equal to 0, it is differentiable everywhere. So, just equate it to 0 to get the critical points. So, the critical points will come from this numerator being 0, which is giving minus 1 and 1. These are the critical points. So, around this point we have to see there is a possibility of maxima, minima and so on. So, we look at the since we have already second derivative, we use the second derivative test for finding extreme points. So, let us look at x equal to minus 1, what about f double prime? So, substituting minus 1 there, we would get 1 minus 3, so that is negative, down is positive anyway. So, x square minus 1 is, this is minus 1 when you take, it will be 1 plus 1 cubed. So, it is 1, f double prime at minus 1. But let us calculate, it is 4 into this is 4 into minus 1 into this is 1 minus 3, which is minus 2 divided by 1 plus 1 cubed. So, this is really 8. So, that gives 2 and 1 2 cancels, minus minus becomes plus. So, it is correct, f of f double prime at minus 1 equal to 1, and this is bigger than 0. So, since this is bigger than 0 and it is a critical point, we have a local minimum at x equal to minus 1. Okay. So, at minus 1 it would look something like this, there is a local minimum. Fine. Then f double prime 1, because 1 is another critical point. So, we evaluate at 1, that gives minus 1, because this minus will be staying 1 minus 3. So, it is f double prime 1 equal to minus 1, it is less than 0. Therefore, it has a local maximum at x equal to 1. So, this is about the extreme points. Then let us look at where f prime is increasing, decreasing and so on for finding the shape of the curve. So, in the interval minus infinity to minus 1, let us evaluate f prime. So, when x is less than minus 1, it is 1 minus, it is something less than minus 1. So, x square will be bigger, this will be negative, right. So, f prime x is less than 0. So, that means f x is decreasing from minus infinity to minus 1. and on the interval minus 1 to 1, so x is bigger than minus 1, but smaller than 1, then this will change its sign. So, you will get f prime x is bigger than 0, that is f x is increasing on minus 1 to 1. Then let us take 1 to infinity, which is the other critical point 1. So, x is bigger than 1, that means this is again bigger. So, it becomes smaller again, f prime x is less than 0, therefore, f is decreasing. So, minus infinity to minus 1, it is decreasing, it is something like this at minus 1, and minus 1 to 1, it is increasing, and again 1 to infinity is decreasing. Roughly it would look something like this. Okay. Now, let us look at where f double prime vanishes. So, as you see, f double prime is 4 x into x square minus 3. So, this is equal to 0 when x equal to 0 or x equal to plus or minus root 3. So, these are the points where f double prime x is 0. So, we should look at the interval these points create. So, we have now 4 intervals for minus infinity to minus root 3. There if you evaluate again f double prime x, that is less than 0, and if you look at minus root 3 to 0, there it is greater than 0, and if you look at 0 to root 3, there again it is less than 0. So, it is changing sign, and if it is bigger than root 3, it is again positive. So, in these 4 intervals, it is really changing sign f double prime x. At these points, they are 0. Okay. So, since it is changing sign around each of these points where it is 0 is a point of inflection. So, there are 3 points of inflection, there the concavity, the shape of the curve is changing at those points. And in these intervals, what happens here? It is f double prime x is less than 0. So, since minus infinity to minus root 3 f double prime x less than 0, it will be concave down. Similarly, minus root 3 to 0, this will be concave up, and 0 to root 3, again it is concave down, and root 3 to infinity, again it is concave up. What about other points? So, other points will be almost similar, but then we should find out where some straight line touches the curve, like your asymptotes, or if x goes to infinity becomes very large, what happens to the function, or x goes to minus infinity, what happens to the function. That would give roughly an idea about what happens for large x. So, suppose first let us see x goes to infinity. When x goes to infinity, you have x is becoming larger, but staying positive, right. So, 2 by x becomes 0, but it is staying positive. 1 by x square again remains positive, but near 0. 1 by x square again positive, and this is 1. So, it is really 1, but positive, right. So, we write 1 plus because of that. It means as x becomes larger and larger and becomes infinity, right, approaches infinity, then f of x will approach 1, but always remain positive. That means, it is really decreasing to 1, right. So, if it is something like x goes to infinity, it is decreasing to 1. So, if y equal to 1 is this line, it will go something like this at infinity. It will not touch, but at infinity only. That is how for large x it will behave. And when x goes to minus infinity, so this remains negative, this remains positive, this remains positive. So, it will be looking like smaller because 1 by x square plus 1. So, it is something 1 by x square plus 1 and minus something. So, it will be smaller than 1, but it is close to 1. So, that we write 1 minus. Okay. So, again x equal to 1, but it will be staying smaller than 1. So, on this side it will be as x goes to minus infinity. So, y equal to 1, let us say that line. So, it may look something like this, right, going like this. When x goes to minus infinity, it will be staying near 1, but smaller than 1. So, that gives the some idea about when x is becoming very large or very small. And if you take x goes to any other c, then limit also remains finite, it is not blowing up anywhere. So, there is a limit at everywhere of the function, right. So, it is not unbounded. So, now you see that the curve decreases to reach the point -1 0, at -1 its value is 0, and increases up to the point 1 2, at 1 it is 2, and then decreases towards minus infinity, the local minimum at x equal to -1, and that is then absolute minimum, because there is no other else, and local maximum at x equal to 1 is an absolute maximum. So, now summarizing all this information, we would say that the curve might look something like this, that at y equal to 1 it will go to meet at infinity, and y equal to 1 minus 1, x equal to -1, after that it decreases. So, this way on the left side. So, it is going this way to y equal to 1, and at these points -1 and 1 there are local maximum and minimum. So, the point of inflection is x equal to -√3 here. So, here it is concave up, and here it is concave down. Similarly, at √3 also the curve is concave down, and here it is concave up. It is go like this, but not going beyond, but this way. So, that is how the curve would look like. You see how the derivatives are used to get an idea of about the shape of the curve.